Hello, in this lecture we are going to study one of the most important ideas in calculus, namely Taylor polynomials. Very often in mathematics and in application we are faced with functions that are complicated. Exponential functions, trigonometric functions, logarithms, or combinations of all of them. Working with these functions exactly is not always easy. So I'm not saying that these functions are complicated, but if you want to get exact values from these functions, that is not that easy. We have to learn how to do it systematically. For example, if I ask you what is sine of 30 degrees, the answer is precisely 0.5. But if I ask what is sine of 37 degrees, we know that answering this question is not as easy as answering the previous one. So this is what type of questions that you are expecting in this lecture. The central idea behind Taylor polynomials is surprisingly simple. Instead of working with a complicated function, as I mentioned above, directly, we try to replace it locally, I emphasize on the word locally, by a polynomial that behaves almost the same way. And the reason we do this is that polynomials are easy to differentiate, easy to integrate, and in principle easy to compute with. The key word here is locally. A Taylor polynomial does not aim to approximate a function everywhere. It approximates the function very well near a chosen point. And the approximation, of course, improves as we include more and more terms into the polynomial. What makes this idea powerful is that it is not just a heuristic or, a graph-based trick. There is a precise mathematical formula called Taylor's formula, which tells us exactly how the polynomial is constructed and also how large the error of the approximation is. This error is measured by what is known as the Lagrange remainder. It tells us how far the Taylor polynomial is from the actual function, and it allows us to control the quality of the approximation in a rigorous way. Okay, let me start with the motivation for the definition of the Taylor polynomial. Okay? So if you remember, we had this before, so consider that you have a function which is differentiable at point A at least, and then this is the tangent line to the graph. So if you remember from the previous lessons, we know the functional form of this L of x. So we know that L of x is indeed equal to f of a plus the derivative of f at a multiplied by x minus a. Okay? But now let us check some facts about L of x. First, let me calculate L of a. Okay, L of a becomes simply f of a itself. So it means that I replace x with a everywhere, so this vanishes and I am left with f of a. But now let me take the derivative of L. Okay, you might say why I am doing this, so please be patient to see why I'm doing it. It becomes clear shortly. So when I differentiate the function L, I get a constant here, yes? Because this is a constant, when I differentiate it, this is gone, and this is a constant, and the derivative of x minus a is 1, so I am left with the constant value f prime of a. But let me also now calculate L prime at a. So this means that I have to replace x with a, but on the right hand side I do not have any x dependence. This function is a constant, so L prime of a will also be f prime of a. Okay, so what you see that this function, first of all, is a polynomial function, because if I consider this to be a, and if I consider this to be b, then I have a plus b times x minus a is my L of x. And then of course you see that's a polynomial of degree 1 because the highest power of x is 1. So this is the structure of L of x. But this is a specific a very particular form of a polynomial of degree 1. The value of L at A matches with the value of f at A, the function itself at A. Moreover, the value of the derivative at A also matches with the derivative of the function at A. So this means that this polynomial is a polynomial that we usually call it has a first order contact with the function. It means the values of the function and this polynomial match at A. Also the values of the derivatives match at A. This is, we say that they have a contact of order 1. Okay? Okay, now you might find it natural to ask another question. If a function f of x is given to us and a point A is fixed, can I find a polynomial of second degree that has a second order contact with my f? What do I mean by second order? I hope that you can guess. So this means that the question is this. A function f which is differentiable 2 times, for example, at point A, okay? So it is differentiable, so don't worry about differentiability of f at the moment. So assume that f is a well-behaved function. The question is that, can I find a polynomial, which I call it p of x, but of degree 2, so that it has contact with f at A of order 2? It means that I demand that p at A becomes equal to f at A, p prime at A becomes equal to f prime at A, and finally p double prime at A becomes f double prime at A. Okay? And then you will see that the answer to this question is yes. More importantly, this polynomial function p of x is unique. So let us explore. So every polynomial of degree 2 can be written in terms of x minus a in this form. So I would say that let us assume that p of x is c naught plus a constant c1 multiplied by x minus a, and then plus c sub 2 x minus a to the power of 2. Okay, so that's not an obstacle. So let me describe why I am choosing it in this way, because the calculations become simpler, but I just want you to understand this is not a limitation. Let me explain this a little bit here. Okay, so let me repeat. You might wonder why I am taking a second degree polynomial in this form. Okay, that's not an obstacle. Let me give you an example. For example, let me take p of x to be this second degree. For simplicity, for example, 3 plus 2x plus x squared. Okay, this is a polynomial. This is the usual second degree polynomial, yes? But let us, for example, choose a to be 3. My claim is that this polynomial, which is written in terms of x, can also be rewritten in terms of x minus a, which in this case is x minus 3. So what is the trick? The trick is to introduce a new variable, say capital X, and to be x minus 3. And then from here you can find x is equal to x plus 3. And then in your polynomial, wherever you see little x, you replace it by this combination. So 3 plus 2x plus x squared then becomes 3 plus 2 times x plus 3, and then I have plus x plus 3 to power 2. Now I can open it up and organize it. So it becomes 3 plus 2x plus 6, and then I have x squared plus 6x plus 9. And if I want to organize it, 3 plus 6, 9 plus 9, 18. And then 2x plus 6x is 8x. And then I have x squared. But now look, if I ask you what is capital X, the answer is x minus 3. So now wherever I see capital X, I can replace it with x minus 3. So it becomes 18 plus x times 8 times x minus 3, and then I have x minus 3 squared. So you see, this polynomial that you have here is exactly equal to this original polynomial of second order that I have. But this one is the standard one, which I now have written it in this form. So this means that my polynomial, which was written in terms of x, now it is written in terms of x minus 3. And I just chose 3, so you can realize that we can just work with a. So this is not an obstacle. I hope that now you agree with me. If I assume that my polynomial p of x has this form, this doesn't impose any limitations to my argument. Yes? Okay, now we don't need this, so let me clean to save some space. Okay, so let me just tell you what we are supposed to do. Motivated by this, we are asking the next level question. If I have a function which is differentiable 2 times at a given point A, is there any polynomial of degree 2 which has second order contact with the function f at point A, which means the values of the polynomial and the function at A match. The same is true for the first derivatives, and also the same is true for the second derivatives. My claim is to show you that the answer is yes, and this polynomial is unique. Now you understand there is no limitation if I assume that my second degree polynomial is of this form. Okay, but now what I want to my demand, I have to actually make sure by fine-tuning these coefficients that all these three conditions are met. So let me start with the simple one. The simple one tells me that if I go to my polynomial, replace x with a, the output should be f of a. So let me do that. I go to my polynomial, replace x with a. As soon as I do that, these two terms are cancelled and c naught is the only term left. But I demand that p of a should be f of a, so the first condition that pa is equal to f of a immediately calculates c naught for me to be equal to f of a. Now let me apply the second condition. So I have to calculate p prime of a. But for calculating p prime of a, I have to calculate p prime of x first, which is very simple. So this is constant, this is gone. The derivative of x minus 1 is 1, so c1 survives, and then plus. Now I can apply the chain rule here, 2 goes down, and then it becomes 2c2 x minus a to power 1, but multiplied by x minus a prime, which is 1. So this is simply 2c2 x minus a. Now p prime is supposed to be equal to f prime of a. P prime of a is supposed to be equal to f prime of a, so it means that if I go to p prime of x, replace x with a, the output is supposed to be f prime of a. Let us do that. I go to my p prime, I replace x with a, this is totally gone, c1 is the only term survives. So this means that c1 is nothing except f prime of a. And finally, I want to apply the third condition, so I need p double prime of x. So it means that I differentiate this once more, and hopefully you agree with me, 2c sub 2 is left, and that's a constant. So if I ask you what is p double prime of a, the answer will not change, because p double prime of x is a constant function. Okay, but then I demand that this equality holds, so this means that this should be equal to f double prime of a. So this means that c2 is 1/2 f double prime of a. And I hope that you see that the derivation is in a way that you are finding c0, c1, and c2 uniquely. There are no other choices for c1, c0, c1, and c2. So this means that finally the answer was p of x equals to, instead of c0 that you see here, I put f of a. Instead of c1, I put f prime of a. and instead of C2 I put 1/2 f double prime of a. So this happens like this. So it becomes f of a plus f prime of a times x minus a, and then finally f double prime of a divided by 2 times x minus a to power 2. So that is the only polynomial that has second contact with the function f at a. Okay, so now as you will see, this function, which is the polynomial of degree 1, will be called the first order Taylor polynomial of the function f about point a. And this polynomial will be called the second order Taylor polynomial of the function f about a. Okay, now let us generalize the question. Let us this time say that, okay, a function f is given to us and a point a is also given to us, but we know that the function f is n times differentiable at a. And the question will be, if you want to mimic the previous two questions, we would say that, is there any polynomial of degree n such that it has contact of order n with my function f, meaning that the values of the polynomial and the function match at a, the values of the first derivative the same, the values of the second derivatives up to the values of the nth order derivatives. Okay, and then you will see that, hopefully you see that with the same method the answer would be yes, and that polynomial of degree n will be unique. Okay, so if you do the same type of calculations, what would be your starting point? Probably you start with something like this. You would say that, let me consider the polynomial of this type, c0 plus c1 x minus a, and then plus c2 x minus a squared up to cn x minus a to power n. Okay, and then what you do, you demand that this polynomial has contact of order n with your function f. So then you apply those conditions, and then one by one you will calculate these coefficients. If you do that, you will see that a very nice pattern appears. So c0 will be f of a, and then c2 will be f prime of a, sorry, c1 will be f prime of a. But f prime of a, I want to write it in this form, f prime of a over 1 factorial. Okay, so and then c2 will take this form, f double prime of a divided by 2 factorial. And then finally, if you continue this, cn will be the nth order derivative of f at a, but divided by n factorial. Okay, so let me just remind you what a factorial is. If n is a natural number, then the factorial of n means multiply n by its previous natural number, and then continue this until you finally reach to 1. So this is n factorial if n is a natural number. For example, if I say what is 5 factorial, 5 factorial means 5 times 4 times 3 times 2 times 1, which of course if you calculate it becomes 120. So that's 5 factorial. There's also a convention here that if you have 0 factorial, by convention 0 factorial is 1. Of course, if you want to understand why this is a good convention, you need to study a little bit of combinatorics. Okay, and one important property is that, for example, if you see 5 factorial is 5 times this product, but this product itself is 4 factorial. So this means that factorial of 5 can be written as 5 itself multiplied by the previous factorial. Okay, so that's a very nice and important relation when it comes to factorials. Okay, so in principle, this polynomial if you do similar calculations here, you will get these coefficients. Okay, so and you see that this 2 is indeed actually 2 factorial, but 2 factorial is the same as 2 times 1, which is 2. That's why you see that 2 appears here. But if you want to do it for the more general case, you will see that the denominators will indeed be 1 factorial, 2 factorial, up to n factorial. And this one indeed is divided by 0 factorial and by this convention. So every denominator can be written as a factorial, okay? So for example, if you see that this index is 2, the order of the derivative is 2, and the denominator you have 2 factorial. And if this index is n, the order of the derivative is n, and this denominator is n factorial. Okay, so this polynomial is called the Taylor polynomial of the function f of order n about point A. Okay, I usually prefer to write t for Taylor polynomial, but I'm using the convention in your book, so this is why I'm using p there. Okay, so now let us go to the formal definition of the Taylor polynomial. Okay, definition. Let f be a function such that f, the nth order derivative of f, exists in an open interval containing the point x equals a. The polynomial p equipped with two indices n and a, x, defined as follows, is called the Taylor polynomial of nth order for function f about a. Okay, so if you see in the previous slide, I showed you that the Taylor polynomial is c0 plus c1 x minus a plus up to cn x minus a to power n. Then we calculated, actually we didn't calculate, we just mimicked the previous example and realized that these coefficients are exactly f of a, and these are the coefficients, yes? Okay, and then of course you can write it as in the form of a sigma. And of course when you write it for the sigma, there is another convention that I want you to remember. If you remember when I was talking about higher order derivatives, I told you that the notation we use for f prime for the first derivative is this one, for the second derivative is this one, for the third derivative is this one. But if I want to go higher to higher order derivatives, for example, order 4, I would write it as f to power, I would write it as f to 4, but I put a pair of brackets around that so it is not being confused by the exponent and the power. Okay, but in that convention, when you see 0 up there, it means that it is the same function itself. So for example, usually in practice it is better to separate k equals to 0 and then write the rest from 1 to n. So in that case, if I replace k with 0, this becomes f of 0a, which according to this convention becomes f of a. 0 factorial is 1, and this expression to power 0 is 1, so it is exactly f of a. So if I write the first term, it is nothing except f of a, then I can write it as plus sigma, the same expression, but instead of starting it from 0, I will start it from 1. Okay, and there is some more terminology to it. Because most of the time we consider a to be 0, it means that we are interested in Taylor polynomials about 0. If that is the case, instead of calling it Taylor polynomial, we call it Maclaurin polynomial. And of course, usually we have to apply two indices for p for the Taylor polynomial because n, which is the order, matters. A is also important. But sometimes, most of the time, might be a is clear from the context. In that case, I just drop this one because we know what a is. Okay, so these remarks in the notes are just what I explained. Let me also emphasize again about this remark. So the nth order Taylor polynomial for a function f about a is the unique polynomial of degree at most n that matches f and its first n derivatives at x equals to a. Namely, it is the only polynomial of degree at most n that has nth order contact with f at x equals to a in the following sense, exactly as I told you before. Okay, why we talk about at most n? Because there might be a function that whose nth order derivative turns out to be 0. Okay, so it means that even though I am talking about the nth order Taylor polynomial, but coincidentally the last term is vanished, it means this is not the case that when I have nth order Taylor polynomial, that polynomial has definitely degree n. So the degree might be n or might be less, but it cannot be more than that. Yes? Okay, now let us solve the first example, which of course is example number 8 in the lecture notes. Determine the nth order Taylor polynomial of this function f of x equals to e to power 2x about x equals to 1. Okay, when you read the question, so it means that the point about which we're supposed to write the Taylor polynomial is 1, x equals to 1, so it means that in this problem a is 1. The next thing we have to know about is the order of the Taylor polynomial that we are going to write. In this problem it is mentioned it is nth order, so n is just simply n. The next thing we do, we write a formula, so it becomes p, n, and a. A in this problem is 1 of x. Okay, so let me write this for the general case and then I will replace it. Okay, so this is the formula we had. So this is equal to, let me write the separated version of that. So f of a plus sigma k starts from 1 up to n, the kth order derivative calculated at a divided by k factorial and then multiplied by x minus a to power k. Yes? Okay, now we know what happens. A is 1. So everywhere I have a, I replace it with 1. Okay, so let us do that. So this means that p, n, and 1, x is equal to f of 1 plus sigma, k goes from 1 to n, the kth order derivative of f calculated at 1 divided by k factorial multiplied by x minus 1 to power k. Okay. But this one is very simple. So if I ask you what is f of 1, it means go to your function, replace x with 1. So what you get is just simply e to power 2. So most of the functions, you have problems in calculating this part because in this case you have to calculate consecutive derivatives of your function. And if the function is not very well behaved function, the derivatives become complicated at every step, so making it will make it harder to find the next derivative. But hopefully you see that this is not one of those functions. Yes, so if I differentiate my function only one time, according to the chain rule, so e to power 2x repeats itself, and then I have to multiply it by the derivative of 2x, which gives me 2. And if I calculate another derivative, it is not adding that much complexity to the problem, because the only thing happens is that another 2 comes down, so it becomes 2 to power 2, e to power 2x. I am intentionally avoiding write 4 for 2 power 2 because I want to see how the pattern goes. If I differentiate once more, another 2 comes down, so it becomes 2 to power 3, but the function repeats itself. And it would be not hard to see the pattern. So if I do it for the kth time, what happens? A k number of 2's will come down. Yes, because you see here the derivative is 1, I have 1, 2. The derivative is the order of derivative is 2, I have 2 2's. The order is 3, I have 3. So if the order is k, I will have k. So it becomes 2 to power k e to power 2x. Okay. But now I have to calculate all of them at point 1. Okay, so this means that you don't need to really calculate it. When you have it in the sigma form, you just need to do the last one. So now if I ask you, what is the kth order derivative calculated at 1, which is exactly what you need here, you go to your kth order derivative and replace x with 1. So you get 2 to the k e to the power of 2. So then it becomes 2 to the k e to the power of 2. And then you plug everything you have back into the formula. So what you can write is that P in 1x is equal to f of 1 is just simply e to power 2, and then plus sigma, k goes from 1 to n. Instead of this expression, you write this. So it becomes 2 to the power of k e to power 2 divided by k factorial, and then I have x minus 1 to power k. So this is the nth order Taylor polynomial for this function. If you prefer to write it in expanded form, that's also okay. So you can write it as the first one is e2. For example, you replace k with 1, you get 2 e to power 2 x minus 1. You replace k with 2, so it becomes 2 to power 2 e to power 2 divided by 2 factorial x minus 1 to power 2. For example, you can replace it with 3, 2 to the power of 3 e to power 2 divided by 3 factorials and then x minus 1 to power 3, but you continue with until the very last, it means the nth order. So it becomes 2 to power n e to power 2 divided by n factorial x minus 1 to power n. And this will be your Taylor polynomial of nth order about x equals to a. Now if I ask you what is the degree of this polynomial, here the degree is also n, because the highest power of x that will appear if I expand all of them, hopefully you agree with me, it is x to power n. So this is nth order derivative, nth order Taylor polynomial, which coincidentally has degree n, because the last derivative is not 0. So this is the answer that you are supposed to provide either in this expanded form or in this sigma form. And of course, you can also collect it into one form. You can start from 0, You can start from 0 to n, and then write it 2 to power k e to power 2, k factorial x minus 1 to power k, because automatically, when I replace k with 0, I get this expression. So if you want, you can write it concisely like this, or if you prefer, write it in the expanded form. So this is the Taylor polynomial of order n for your function f of x about x equals to a. Okay, it would be a good idea if we see what we are doing using a free application called GeoGebra Classic 6. So what I do, I will first draw the graph of this function that we were investigating the first example in our lesson today. So this is the graph of this function, and I will type Taylor, so I will get a suggestion. So I will choose this one. My function is f, so I call it f, that's the function. The x value here is the a value in our example, which was 1. And then if you don't mind, let me just type n. You'll see what happens when I press enter. GeoGebra doesn't know anything about n, so it will think that, okay, n can take different values. And of course, wrongly it chooses, this is by default from -5 to 5. I can do some adjustments. I go to settings, a slider, so I will start with 1. And then, yeah, 5 is probably good. And then the increment means that, because this is an integer value, so I cannot have some decimal numbers in between, so I put increment as 1. It means that from 1 you jump to 2, from 2 you jump to 3, etc. So if you don't mind, let me see, I don't know how much it can calculate, let me give 10, and then go here. Okay, so press enter, and then I close to see what happens. So now n is 1. So it means that GeoGebra is calculating the Taylor polynomial of order 1. So of course, that's not surprising. This is the tangent line. So because we are focusing around point 1, so let me zoom a little bit here. So let me rescale it a little bit so that it becomes clear what we are doing, because of the point of interest for us is x equals to 1. So you see what is happening. This blue line here is the first order Taylor polynomial, which in this case, of course, as you learned before, is nothing except the tangent to the curve exactly at the point x equals to 1. Okay, so it's already a very nice match between the function. You see the deviation becomes bigger and bigger as we are going farther away from point 1. But approximately when we are close to 1, so here, around here, you see that they have a very good match. But the point is that when I increase the number n, where I am looking into a higher order Taylor polynomials, this approximation of the blue line or curve will be a better and better approximation to the graph of the function. So let us just do this and see what happens. So for example, I increase n, so this is now 2. Now you see that this is a blue curve now. It's a parabola. The equation is this is generating. And you see, I hope that you can see that we are getting a better approximation around the point 1. I hope that you can feel it, yes? So if I increase it, this happens. If I increase it, yeah, it's not surprising. You see, this blue curve is actually start lying on the real curve more and more. So you see it is really working, yes? So that's the idea. By going into higher order Taylor polynomials, we will have a better and better approximation for the real function. Okay, but that was also good to see. Okay, so might be that's a good idea if we stop here. My intention is, if possible, on the weekend I will continue actually making new videos so that we can have a complete video for the lecture notes that I have produced for you before. Until the next video, be safe and goodbye. Thank you.